Hi Europe, Amsterdam is a bit too small to say. Welcome to this talk on a niche topic, PHP long-running processes. I'll explain in a bit what I'm talking about. I'm Giorgio. I am a software engineering test, a bit of a cross between a developer and a tester. So I care a lot about the QA and ops side of things, not just about writing code and putting it on some server. I work on distributed systems, mainly composed of services or microservices. I try to cook up automated test suites, continuous delivery pipelines, pasta and risotto sometimes, not ice cream usually. So if you take a look at the server application programming interfaces for friends, SAPIs of PHP, you will find many different ones. The popular ones that you will use every day are the ones based on Apache or FastGGI, which is used by PHP FPM, for example, and of course the CLI SAPI, which you use every time you run PHP unit or composer or thing or any kind of PHP command that you run in your terminal. If you take a look at the kind of processes that you can write that use the CLI SAPI, you will find that many of them are just scripts automating some task. You can consider even PHP unit as a large script using lots of classes to pull all your tests together and run them. You can consider Composer still a script. But you also have other kinds of CLI processes like cron jobs that you deploy on a server, you schedule them to being run every hour or every minute or every day in order to accomplish some task. And you also have another kind of process that you deploy on servers, the long-running process kind. If you take a look at the difference between these CLI processes, you'll find that scripts usually run in seconds or minutes, or if you have a very long build, in hours. They take some input from the standard input that you have in a terminal, and they write some output that you can take a look at to understand what is going on in your PHP unit or composer command. While crons and long-running processes are different, they have no user interaction because with a cron there is no one there looking at the output, there is no one giving some input by key presses. And the main difference, however, is that crons are designed to run for seconds at best, for minutes, really not for hours because they will be not without control at that point, while long-running processes are designed to run for long. Not because they are slow, but because they will always be there to provide low latency response to something that is happening on your web application. Quick examples of long-running processes you may have written in PHP. All kind of queue workers, if you're using RabbitMQ, ZeroMQ, SQS, or other proprietary queue systems, you will have to set up some processes usually that pick new messages of the queue and that do something with that, usually triggering new transactions on your application. German workers are a conceptually different, but in practice quite similar example. The queue is internal to your application. It is a job server of things to do. For example, a bunch of images to resize, and you can write processes that ask German for new jobs to do and then execute them in the background. You can even have more exotic usages of long-running processes like generating database views yourself by having something polling the database for new data. The efficiency of this varies depending on the database, and then write the results in other tables. All these are PHP long-running processes. They stay up. They are not part of a web server like Apache or PHP FPM, but are started on the command line. And in general, the user does not interact with this, at least directly. The essential characteristic that you can extract from these categories of processes I just listed is that they run for hours. They are supposed to run for hours. They can run for days, typically until the next deploy, because at the next deploy, you have to change the code, and so you have to restart them. You usually scale them not by making a single process more efficient, but by instantiating multiple copies, all implementing a pattern called competing consumers where they are fed from the same source. And usually they are not the child of a web server at all. They are, these processes in the Unix sense are children of another daemon that takes care of starting them and restarting them when needed, or if they crash. So this is something for which you may not necessarily want to use PHP. It's not exactly built for this kind of essentially small daemons. In fact, the multi-process model that PHP uses for parallelism is not very efficient, because in every new process that you spin up, you will have a full copy of all your global data, of all the memory that is allocated by the PHP interpreter. In languages where you are multi-threading, like Java, you can share a lot of memory between the different threads of your application instead. There is really no standard supervision or system or framework that you can use to put these processes under the umbrella of something that monitors them. There are, in general, supervision systems that may be used for PHP processes, but nothing specific and optimized for them, like PHP FPM does for the web version of these processes. And there is not even much fault tolerance in the PHP interpreter, so there are some fatal errors you will never be able to catch. Some of them have become catchable in the latest versions, but in general you can pretty much encounter a segmentation fault and not being able to recover inside the same process. You have to have other strategies on top. However, PHP has lots of advantages for you, conditioned to the fact that you are a PHP developer at the PHP conference, so your application is probably already written in PHP. You use libraries, lots of open source libraries that you know very well, that are written in PHP, and you probably also have some private libraries inside your company that can be shared between the projects or the services that you're writing. And you don't want to start from scratch in another language. You have deployment tooling that is able to bring new copies of your PHP applications onto servers and to do whatever is needed to transition from one release to the other. Deploying a new closure application will be a whole new thing for you. You know the language, the PHP language very well, probably have been using it for several years. When I'm talking about knowing a language, it's not just about knowing how to write an hello world or a new route into your preferred MVC framework. It's about knowing the ins and outs so that when something goes wrong, you know where to go, how to fix it. In general, what you gain by all this combination of factors that PHP gives you by being already so entrenched in the work you do is that you get the ability to move the existing functionality that is in your website or web application into the background, into long-running processes, with some improvements on the latency that users see, because very heavy things like resizing images, my favorite example, can be moved off. This is the minimal structure that I extracted from writing many different long-running processes over the years. The start is no different from a script. You have the PHP interpreter being chosen as the one to run this. You have a bootstrap that has to be included. And then we have a main loop. This main loop has a condition for stopping, which we can check in order to see if we should just exit with the zero exit code or we should go on iterating. Every new iteration of this process is usually a new transaction that we can perform on our database, or a new image that we can generate, or in any case, in a new job that we need to perform. The phases of a single iteration are picking an item from a queue or a job server, doing something with that item, and committing that item to the job server or the queue, saying that we have finished working with it so that no other process will pick up the same item. It won't be needed to, it won't be processed again. The picking of a new job, a new item, is usually limited to a timeout, so that this blocking call does not last forever, but in case there is no new job to pick up, this item variable will become null after the timeout, in this case of 20 seconds, and we will be able to skip essentially this iteration and go to see if we should stop. If we have a blocking call that we are never able to exit from without a timeout, we will then not be able to reach this stopping condition when we are, for example, in the process of restarting this gracefully. If we have a timeout, this after a while can become null, and we can go to should stop and checking our exit condition. Otherwise, any signal will be stuck on the blocking call, and the process will be usually, depending on the supervision system you use, be killed ungracefully, possibly interrupting work after a certain external timeout. So this is a general pattern, a general structure. There are many problems that then come up. Originally, this talk was 30 minutes long, so I had to pick. But fortunately, there are so many problems that we can fill an even longer talk. And what I hope to do today is to give you some standard proven way of solving these problems. The first of the problems, and one that you should definitely outsource, is the problem of supervision. One way to start long-running processes is to go into a server, run with no app or with screen a PHP process, and then try to go away and leave it there. This is not a very good way to deploy a long-running process, because in case of crash or of any problem in that process, no one is there to see it, to restart it if needed. The main job of supervision system is to monitor your process to see if it is killed by the operating system or crashed for some internal error, and to restart it if needed. But supervision is not just about simple restart. It's a more complex problem. For example, you may have a very dangerous, I would say, but an error that you cannot recover from automatically, like a class not found because you have a botched deploy, some file is missing, or any other kind of persistent error that restarts cannot solve. You can solve an out-of-memory error for that, some out-of-memory errors by restarting a process. You can solve a temporary error on an API call not being completed with a restart, but you cannot solve a class not found. So supervision systems, for example, try to implement strategies where they restart a process for a certain amount of times inside a certain time interval, for example, 10 times in 30 seconds. But if they have to restart it too much, they just stop and fire up an alert, because evidently the restarting is not working. So supervision is not something so simple. It seems simple at first, just to restart everything, but it becomes more complex. So I advise always to outsource the problem of supervision to another daemon. The most common daemon that works everywhere is supervisor D. It's written in Python. You give to supervisor D a configuration of which process to run, how many copies, where to write the standard error and the standard output of these processes, and it will keep them up. And then the supervision system provides some primitives that are able to restart or to stop these processes during deploy. If you are on Ubuntu and probably also on some many other Linux system, you have some more specific options. Upstart and systemd are the init replacement. Init is the original process that starts everything inside a Unix operating system, the one with PID 1. And upstart and systemd replaced it. Systemd replaced upstart in the newer version of Ubuntu, and systemd is being adopted in many other distros, the Debian-based, but not just them. So you can put your PHP processes under the supervision tree of upstart and systemd instead, which means they will run at the same level at which Apache or PHP FPM or MySQL or all the other daemons are run. The deconfiguration is a bit different, but it's not as complex as it was with the init system. It's mostly a declarative configuration, like in the case of supervisor D. This is our first problem that hopefully when we solve this, we will keep up our processes for as long as possible. However, the next problem is stopping, because it's not just about killing the process with a sigkill in a Unix environment and then be done with it. If you are halfway through a job, you probably don't want to just interrupt what you're doing. For example, leaving some rows on a database written and some other rows related to the same transaction not being written instead. You will have to roll back the transaction, but you may run into other problems, like the fact that you have state that is not just in a database, you have files that have been written somewhere, you may have done external calls. So you should always be able to recover by a long-running process that is killed abruptly by a seed kill, but it's best if you devise ways in which you can restart that process gracefully, which means not while it is inside the main loop, but between one iteration and the other of the main loop, so that the jobs that it is performing are almost always performed atomically. You don't have to apply many recovery strategies. The way to do this on a Unix environment is to catch signals. Signals are the way, a standard way in which the OS communicates with your processes, and sig term is usually the signal that is used by supervision system to tell the process that it should stop. In PHP, we are not multi-threaded, so we have a single thread of execution. We have to check for signals from time to time, and usually I do this in the stop condition of our while main loop. How do we access these in the standard PHP library? There is a couple of primitives. PCNTL stands for the process control extension. So we define a signal handler for the sig term signal. This signal handler is just a closure. This closure has a reference to a Boolean. In case it was an object with a state, you don't even need the reference. That's secondary. And it sets this flag, this should exit flag, to true when the process is delivered. When the process is actually delivered, when we call process control signal dispatch. So this code in the closure won't be executed at any time. It will only be executed when they explicitly require it by requiring a signal dispatch with this call. If we do this at every iteration of our main loop, we are able to exit gracefully with in a time that is up to the timeout that we set inside the polling call. Usually, the duration of an iteration of the loop is up to the polling call. In our case, we set it to 20 seconds, for example, plus the work that has been to do. That has to be done on the item that we have picked from the queue or from the job server. In that case, it means that usually in 30 seconds, we can do any deploy, because we can send sig term signals to all of our processes in parallel. All these signals are coded. This process then stop because the should stop condition become true and we exit from their main loop, and then the supervision system will restart new copies of the process that, in case of a deploy, are using new code, for example. So we already see why the combination of having an underlying supervising system is very useful for other problems to solve, like the graceful stopping that we're seeing here. The next problem is memory. So you can chase memory leak as much as you want, but sometimes you have a giant stack of the code where you include different PHP extensions talking to different databases or other services, and on top you have libraries and loggers, and a very big mountain of code that is leaking memory somewhere. So you may see that the occupied memory in your processes goes up and up and up. It may go up slowly. It may go up linearly with the amount of jobs that you are processing, but it is going up. My solution here is not trying to optimize the memory usage. It's just to do essentially what is a graceful restart when needed. So in our stopping condition, we can use the PHP standard library to check the memory usage. Memory get usage is the function that we are going after. With the true argument, we see the amount of memory that is actually allocated to the, through the operating system, not the amount of memory that is used by variables. So it is a larger approximation of the memory that is actually used, but it is a good approximation. And whenever we see that this memory usage is greater than the maximum we are going to allow, then we can say, well, we should stop, and the new copy of the process should be restarted by the supervision system. Why we do this? because that way we will see not a large amount of memory being occupied by the process, but we'll see going up and being restarted, up and being restarted. For example, I do in an application, an internal application, that we have an import of a very large for that database amount of data, and I see the processes continuously being restarted every few minutes while I do this import in production. I don't have to do anything. Without these restarts, they will soon saturate the memory of the servers I'm running them in. But with the restarts, it's a very recoverable way of working. There is no problem because they continuously restarted to have an empty memory segment. So we have seen supervision, graceful restarts, and memory, but there are even more problems that can come up and that we should be aware of. Global state is one problem that comes up in your test suite very much, because your test suite is a process, hopefully not a very long running one, but it is doing lots of different transactions on lots of different data, all inside the same process. So some global state may spill from one test to the other, and the same is true in long-running processes in production, where you may have a global database connection, and a connection in itself is not a problem, but if you leave transactions open on that connection, it can be, because data get committed inside the wrong transaction, or you may get errors on aborts or on commits. You may have singletons around, God forbid them, where the customer data are inserted into a singleton, and then you go operating on some job for another customer, and private or in any case wrong data spills over in the next job. You may have even subtler global states like the doctrines entity manager, which gets closed at the end of something you're doing, and then you need to create another one to reopen it if possible, so that you can continue to work in the same process. Global state in general is not a problem if it is immutable, but if there is anything immutable that can be carried over from one process from one transaction to another inside the same process, then the problem comes up. So here the standard advice that I would say to everyone with a test suite carrying around global state applies. Don't use global variables, don't use singletons. Try to isolate the scope of your job so that you can freshly create everything you need inside the single transaction that you're working on into your long-running process. Do not carry over the data that you shouldn't be carrying over. Only carry over things that are immutable, like the classes that you have loaded in the bootstrap. If everything is running correctly and no one is paging you at night because the processes have crashed, then we may have the nice problem of running into bottlenecks, which means your application is good, it's working well, but it has some performance problems. One of the first bottlenecks you encounter is that of PHP single threading. We are not in an environment like Node.js, where we have many problems with the callback L, but we can do many API calls simultaneously very easily. We are not in a multi-threaded environment like the Java virtual machine, or even a liked green thread environment like the Erlang virtual machine. We are in PHP, we only have a single thread of execution. We make an API call that takes 10 seconds, the process is stuck there for 10 seconds. The way to do this in PHP is to apply brute force, that always works, and to create more than one instance of the same process, so that if one is stuck on an external slow API call, the others are able to make progress. When you start creating more than one instance, of course, you may run into a memory pressure situation. So usually I allow the processes to take as much as 64, 128 megabytes of memory each. When they reach this limit, try to restart them. So you can have, for example, 10, 20 of these processes very easily on a small server. Then, if you want to expand more, you should do horizontal scaling. have the process being fed from the same source, the same job server, the same queue. Usually these systems are built with scaling for many consumers in mind. And you can scale horizontally by adding more servers, each server containing multiple copies of the same process. A similar bottleneck that you may run into is not that of memory, but that of CPU. This is only true if your processes are doing something that is actually CPU intensive. Image resizing, again, comes to mind. If you're doing external API calls, CPU is not a problem because your process is stuck in a IO wait state all the time. If you're doing something that uses the CPU like machine learning or image resizing, video transcoding, whatever, usually the things that you do with exec that offload work to a C-optimized process, then in that case, you may have CPU bottlenecks. And here, again, the same solution. You can horizontally scale, you can use multiple servers, you can use server with many CPUs at the same time. And this is really the only way to optimize throughput. You still will not optimize latency so much because even with the kind of huge beefy machines that you can get on AWS or in cloud environments, they will have maybe 16 cores, so you can have more, you can have a CPU usage which goes up to 1,600%, but still they're slow cores. So these are suggestions for scaling throughputs more than latency. Finally, if you have optimized all of this, you may run, or no, if you have not optimized all that, but your queries are very slow, you may run into the bottleneck of the database you're reading or writing to. You're picking jobs off from a queue, but usually there is some state you need to store in the database as a result of the job, even if all from a domain, from an event logging perspective. If you're having problems at the database level, you go for the usual profiling. You can see the queries that are being performed. You can set up a monitoring system like New Relic that try to collect the slowest queries to see where you have the most bang for the buck and where you should optimize. You can try to introduce caching. There is nothing different from the usual database optimization. And if you have optimized also your database, you basically won. At that point, you are depending on the rate limit of external resources. So maybe you are posting images to ImageU or another service, or you are committing files to GitHub. You are at that point bottlenecked by the rate limit that external service allows you to use. So you may not have more than several thousands calls per minute because that's what they allow you to do. At that point, your problem is not technological anymore. It's more business-like, social, obtaining better conditions. So at that point, I will stop and I will leave the work to someone else. We may want to use some ready-made tools to manage, at least manually, or to speed up finding the search for problems that are happening in our production system. Actually, some tools are very simple. Some are very complicated but can be outsourced. So a very simple one is the PS utility that is installed in every Unix server ever. PS by itself doesn't do much, but with the right switches, it gives you a very long, sometimes noisy output of which user a process is running as, what was the original command line that was used to start it, the state in which the process is, whether it is waiting on a blocking call like an API call or a polling to a database, or whether it is actually running and occupying CPU time. So PS is a wonderful tool. You can just log into a server and see the whole picture very easily. And that's a simple tool. A very complex tool instead is New Relic, for example. External service, you have to install daemons in order to use it. I'm sure the implementation itself is very complex in the amount of work that went into coding these daemons to collect information from your operating system and shipping it to a server that may be on the other side of the world, but you cannot source that, so it's no problem. It is a problem of money if you're using some advanced features and you have to pay for it, but New Relic provides application performance monitoring, which is their word for monitoring your services rather than your servers, and actual server monitoring. On the application monitoring side, you may annotate your processes so that you see the rate at which they are processing new jobs, which are the jobs, if you categorize them, that are taking the most, which are the resources being used by that particular job, whether it is CPU or whether it is an external call to the database. On the server side, instead, it provides you with the usual measurements of CPU, memory, disk I/O, whether the disk is being filled, and so on and so on. Simple stuff, but aggregated across your population of servers, so very easy to use in that regard. In the application side, instead, there are many libraries that you can use. Symfony Console is the first that comes to mind. Symfony Console itself has a part that is dedicated to user interaction. You won't use that in a long-running context, of course, but all the parsing of arguments, for example, is so easy to use that it will be a mess to rely on anything that has a lower abstraction level, like the standard library of PHP itself. You just define new processes and new classes. What do you want more from life? On top, you may decide to use your own private libraries, especially if you are sharing these processes between many services or many projects in your company. You should definitely introduce some private Git repositories that store the usual boilerplate patterns that I show you here, adapted to your own context, and that you can deploy everywhere you need. I put in these slides that are already online, and I will link later, some resources because it's easy to talk, but people should always say, show me the code. And these are links to some open source code from my company, where we wrote some processes that were exiting on exit term, and the same processes checking conditions for exiting on memory limits. So it's what I've shown you, but in a larger context where there is actually a real process making use of the code. It's not a snippet, it's a real application. Some other pointers instead are for the supervision system configuration. It's a bit like with frameworks, so you have to know the ins and outs of the supervision system that you use, because it will limit the things that you can actually do with your processes. For example, there are usually some limitations on the dynamicity of the number of processes that you can use. With Supervisor D, usually you have a fixed amount of number per server, and you have to change the configuration in an invasive way to be able to change that number. With Upstart, instead, you are more dynamic. You can scale up or scale down the number just by running some commands, but you will have to automate those commands yourself. So there are pros and cons to the different systems, and you really have to study them and use them for a while in anger before you're able to judge for yourself. So my conclusions here are: PHP long-running processes can work well. You don't have to write them in Erlang just because it's cool, or in Go, which is the newest kid on the coolest kid on the block. However, you have to carefully work on the operations, on the testing of them, on managing them in production. You cannot just write a script, start it on a server, and go home, because problems will appear. You have to know your limits, especially in a language like PHP. You have fundamental performance limits, but you don't want to rewrite it in C to have a better performance. You have fundamental efficiency limits on the amount of different processes that you can run for megabytes of RAM, for example, because of all the memory that gets replicated between processes in PHP. There are limits, but you have to know them. You can work around them by scaling horizontally, usually. And finally, I think that the cohesion of simplicity of writing a microservice or a service or an interweb application as with a single language, take JavaScript away, the simplicity of keeping all of your team being able to work on it because you didn't choose an exotic language, but you choose PHP, which everyone should already know. All this simplicity wins over the technological terror of writing an application in 5 different languages, each being the best tool for the job, but each carrying around also its own problems. Thank you for coming here and for listening to me.